so the next one is, remember we prove a theorem that if Fn converges to F in distribution, then its characteristic functions phi n will converge to phi. Now we want to look at it another the inverse direction. So if we have a sequence of characteristic function phi n that converge pointwise to a limit function phi, and the limit function phi is continuous at 0, then the associated distributions Fn is tight. So as long as this phi, the limiting function phi, is continuous at 0, then we can conclude that Fn is tight. Furthermore, Fn will converge to F when where F is the distribution function of phi. So let's prove that. So what we want to prove is that first we want to prove Fn is tight. To prove Fn is tight, we want to prove that this, by the definition, this 1 minus Fn plus Fn on some constant value can be made as small as possible by choosing some the constant properly. So by that, if we look at this integral here, we'll see how that will help us. So the integral of from minus a to a of on 1 minus e to the power itx dt, which is, by rearranging that, which is just a value of 2a minus 2 times sine ax divided by x. And if we divide both sides by a and integrate over dfn, which is a double integral on this function dt and dfnx. But since 1 minus e to the power itx is bounded, it's a complex number, it's bounded, and the integrable on the bounded interval minus a and a, and further the dfn is a probability measure, so the whole integral is integrable. So by the Fubini theorem, we can exchange the two integrals we first integrate with respect to Fn and then integrate with respect to t. Then our integral of 1 over a, and integrate from minus a to a, so the inner integral here will becomes 1 minus phi n t, and then dt. And same over here, if we integral with dfn, that's what we have here. And since sine ax is less than equal to the absolute sine ax is less than equal to ax, then this one is 1 minus sine ax divided by x is always greater than equal to 0. So this one, if you look at this one it will be just, it will be greater than equal to, we will replace that with 1, it will be greater than equal to this one, 1 minus a divided by epsilon over ax. And if you integrate on a subset for x epsilon of x greater than equal to ax, greater than equal to 2 divided by a, if you do that, you see 2 divided by a, then this one will becomes has value of 1, and has a maximum value of 1, and so this will be greater than equal to the integral, and we can replace the integral here to be 1 and dfn, and that is just the definition of 1 minus fn 2ax, 2 divided by a, plus fn minus 2 divided by a. So this, what we have done right now, what we have done so far is this one. The integral here is greater than or equal to this one, and we want to prove that this can be made as small as possible by choosing a properly. So there's one more condition we haven't used, which is the function phi is continuous at 0. So if we look at the same integral here, integral of minus a to a, so if we look at 1 over a times the integral of minus a to a, integrating on 1 minus phi t, this is just so this integral here will go to 0. This will go to 0 as well as a goes to 0. So we have to use the L'Hopital's rule, and by doing that, we conclude that this limit will go to 0. Therefore, we could choose the a such that this a inverse, so 1 over a times integral of a minus a of this function is to be less than some epsilon, right? So we have a bound. We can choose. So that's the a. Let's say we choose a, and that is less than epsilon. Now we come back to our function here. We have this one is less than equal to greater than equal to this one. So that's what we have here. But then we want to make this to be less than some epsilon. To do that, remember we haven't used the condition phi n converge to phi for all t. So by the dominant convergence theorem, y is dominant convergence. We're integrating from on a bounded interval with a bounded function. So by phi n converges phi, then this integral will converge to this one. So we can find that capital N, a number n, such that for all n greater than n, the difference of these two integral can be less than or equal to the epsilon that we want, the epsilon, same epsilon of this one, same epsilon as the one we choosing a. So by doing that, rearranging this one, so we'll move this one to the other side, to the epsilon side. That's what we got here. So this will be less than equal to epsilon plus this integral. And remember, we have chosen a such that this will be less than epsilon. So that will be less than equal to 2 epsilon. So the a we choose here can be made to be less than or equal to 2 epsilon for n large enough. So the lim sup of that for n large than n. So for the lim sup, this will be less than 2 epsilon. Since epsilon is arbitrary, Fn is tight. So now that proves Fn is tight. Now we want to prove that the Fn converges to F for some probability distribution F. So we want to prove that. We want to prove that for any. So now we are using Pomental lemma again. So to prove that is a converging distribution, we want to prove that for any continuous and bounded function g, expected value gxn converge to expected value gx. Remember, from the real analysis, we know that um, a sequence converges to a number if and only if every subsequence there's a further subsequence that converges to that number. And remember the Hellis selection theorem that for every subsequence f and k, there's a further subsequence f and kj converge to f. And since fn is tight, we know that f is a probability distribution, and so this f is the probability distribution and has a characteristic function phi. That's what that's our assumption, right? And so every further subsequence converges to, but since so now we have that every further subsequence converges to the same f, because the phi and kj converges to phi for every further subsequence f and kj. So f and because all f has the same distribution, same characteristic function phi, by the condition phi n converges to phi. Therefore, the convergence sequence we want to prove here. So we have then the sequence of integral of gx on df and k. So every subsequence f and k, we have a further subsequence that will converge to the integral. So what I mean is that there's a further subsequence of where integral of gx df and kj converge to integral of gx f df. That's what we have in here. So we have this. So we have the integral of gx f and k converge to integral of g df. And since this is true for every for the subsequence, we have fn converge to f in distribution. So that completes the proof of this theorem, and that will help us. So those theorems will help us to prove the central limit theorem that I'm gonna talk about right now.